Hi everyone, welcome to the International Methods Colloquium. The International Methods Colloquium, or IMC, is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Mark Nieman from the University of Alabama. Welcome, Mark.
Thank you for having me.
You're quite welcome. Thanks for being here. The talk is entitled Statistical Analysis of Strategic Interaction with Unobserved Player Actions, Introducing a Strategic Probit with Partial Observability. So if you're still hanging on after that title, you're in the right place. Mark's talk will last between 30 and 40 minutes, after which point we will take our questions from the audience. You may call in to ask a question on air at our toll-free call-in line, which is 1-855-667-8287. That's 1-855-NO-STATS. You can email questions to methods.colloquium@gmail.com. Finally, you can ask a question using the GoToWebinar Ask Question dialog box that appears on the GoToWebinar control panel. For our viewers outside the United States, we recommend using the Ask Question box to ensure that we receive your questions immediately. A copy of the slideshow that goes along with this presentation will be available at a link that will be posted in a few minutes on that, well, there it is, in the right-hand side box. Without further ado, I'd like to welcome Mark to the International Methods Colloquium. Welcome, Mark.
Thank you for having me again. Thank you for tuning in, everyone. So what I'm interested in looking at this is that strategic behavior is ubiquitous to political science, and increasingly there's been attention paid to empirically modeling these strategic interactions. These empirical models tend to look at, or try to look at, how one player's actions may be affected by what they expect another player to do. Unfortunately, much of the data within political science is structured as outcome rather than actor-specific. To give an example of this, a lot of our data collection is done without much consideration to the underlying theoretical process. The correlates of war, for example, were actually started with the explicit rationale that they would avoid being guided by one theory and instead permit testing of various theories. And while that's a great goal, this means that much of the data is collected in a way that we only see the outcome of a war rather than the escalation process that leads to that outcome. The goal of this project is to derive an estimator based on Signorino's strategic probit that probabilistically estimates unobserved actor actions when we only know the actual outcome. To give an example, we can think of the Civil War as a strategic interaction. In the first stage, an opposition group decides whether or not to choose action A or not A. If they choose not A, then we see the status quo and there can be no civil war. If we see action A, which we can think of as a challenge to the government, then the government can respond by choosing action B or not B. Action B can be thought of as a repressive action in response to that challenge. If both the opposition and the government choose A and B, then we observe a civil war. If the government chooses not B, even after a challenge is initiated, then we would observe some kind of acquiescence to that opposition group, and that would be coded in the typical manner as a not war. But these status quo and this government acquiesce are two very different, qualitatively distinct outcomes that are being pooled together as not war. Another example we can think of is environmental fines as a strategic interaction. In the first stage, a firm can decide whether or not to pollute over the legal limit. The EPA then either detects this and fines the firm, or it fails to detect this and issues no fine. In order for a fine to be given, a firm has to both pollute and be caught. Now, the probability of being caught likely affects whether or not that firm chooses to pollute above the legal limit in the first place. This matters substantively because if our data is only collected on this joint outcome of fine or not fine, then we would code cases of no violation and cases where the EPA simply fails to detect violations as zeros and fines as ones. And this leads to very different policy outcomes if we think that firms are simply not polluting at all, or firms are polluting rampantly and they're simply not being caught. So we can think of this as a theoretical process, a strategic interaction, where player one chooses action A or not A, and that choice depends in part on what they expect player 2 to do. They're going to choose B or not B. So we can think of this as each player having utilities on each potential outcome. In the choice of player 1, their expected utility of action A is going to depend on the probability of what player 2 is going to do. So we can think of these following kind of the typical strategic Probit or logic process, the QRE model, as each outcome having an observable component and an unobservable component, where the unobservable component is either private information or actor error or something along those lines that follows some specified distribution. The way we typically solve these models is that we calculate the probability of each action, where in the first stage we use backwards induction to help solve this. So we calculate first what player 2 is going to do and use those probabilities to figure out what we think player 1 is going to do. So if we calculate the probability of action B occurring, we simply take the utility for outcome Y4 and subtract the outcome from Y3, some level of certainty. And we take that probability and plug that into an equation where we look at the probability of action A occurring, which has to account for both the probability of B occurring at all, so that the first term is the action of taking A, the probability of B times the outcome Y4, 1 minus the probability of B for the outcome of Y3, that all is taking action A, and you subtract that from taking action not A over some level of uncertainty. The equilibrium of this, of course, Y1, the probability of Y1 is simply the action, or the probability of not selecting A, so this just depends on player 1, although it also is conditioned by that expectation of player 2. The action, or the outcome Y3, the probability of that is going to be that we saw action A, and then the probability that we saw action not B, and then finally Y4 is that joint probability of A and B. The likelihood takes the form in equation 6, where we're simply looking at the outcome. We're looking at each individual observation to see which outcome we observed. This is just the typical strategic Probit that Signorino introduced, and is pretty well known in the field at this point. However, a problem exists if we don't have information on each player's decision, if we don't actually know what each actor did at earlier stages. Again, turning back to the example of civil war, we typically, in our correlates of war data set, we don't know that an opposition group challenged the government. We don't have data on that. We only have data on if both action A and B occurred. So there's several potential solutions to this. The first one is that we can attempt to collect more data, which is always a good thing. Now, the problems with data collection efforts might be that we have financial and time constraints. We might not be able to get that NSF grant to hire all the RAs that we need to take this effort. We might have time constraints that this, if we're trying to go back too far in time, this might take far too long for us before our tenure review. If we may have coordination problems. We might think that there are people out there who can help us collect this information, but we don't know how to find them. We may have language limitations to properly collect the Civil War example. We would have to collect this data on all areas. Simply using a LexisNexis search may not be enough, that we would need to account for foreign languages that may be overlooked using typical English-only newspapers. And there may even be problems where the data simply no longer exists. If we turn back to the EPA example, firms are very unlikely to give us data on when they were not punished for a violation. They're not going to tell us when they violated the law. In the Civil War example, we would need to have dyadic data on all non-war observations. So groups that chose not to actually challenge the government, not just the groups that selected into the subset of civil conflict into that sample. Existing estimators are also problematic. If we use a traditional Probit or logit, we're treating this strategic process as additive rather than conditional. If we use a split sample Probit or logit, where we're going to try to identify two distinct types of player one that never engages with player 2, which would be the zero inflated equation, and one where we're saying this group is relevant and they engage in the Probit or logit equation. Now the problem with the split sample models is that they're not actually strategic, and that the actions of player 1 are independent of player 2. They're not conditioned in any way. Essentially, that second equation is just a traditional probit or logit that is treating the actors in an additive, or treating the regressors in an additive manner rather than conditional. What I propose instead is using a strategic probit with partial observability. In this model, we're saying it's partially observed because our outcome variable depends on the joint actions of at least two previous actors, and the outcome actions could be due to one actor or the other. But in order to see any outcome, both actors have to engage in specific actions. In this case, we're going to say that the outcome equation is the same as before, but where y1 is going to be the joint action, the probability that A occurred and the probability that B occurred, whereas y equals 0 is going to be the first term representing that status quo outcome, where 1 minus PA, so the action of not A, plus a probabilistic estimate of the probability that action A occurred and the probability that action B did not occur. So we're going to be trying to pool these in a probabilistic manner. The advantages of this approach is that we're following the strategic probit and the strategic kind of underlying data generating process that is so common in political science in general. We're using the observed utilities. We're going to use the regressors to help separate and identify the different types of zeros, the qualitatively distinct zeros of either the EPA not issuing a fine because they were duped, or not issuing a fine because nobody did anything wrong. A civil war not occurring because nobody challenged the government, or a civil war not occurring because the government acquiesced and there's been a qualitative change in the relationship between the government and that opposition. In contrast to the zero inflated model, this explicitly accounts for strategy in that the expected behavior of both players is present in the equations. The second type of zero is going to be captured by having that joint action of A and not B for kind of getting that second type of zero. And in order to actually observe an outcome, we have to have both probability A and probability B in equation 8 from the previous slide. I would create a set of Monte Carlos following a strategic data generating process to compare the probit model, a split sample probit, and the strategic probit with partial observability. The data generating process is clear from the figure, in that we're going to have two types of zero that are pooled together that we cannot distinctly identify, but we know from the data generating process that they're present, whereas we only observe an outcome where both actors, where player 1 chooses A and player 2 chooses B. So the kind of latent variable y is going to be, it's going to take the form of y1 when player 1 prefers the outcome y1 over the outcome y3 when player 2 prefers outcome y3 to outcome y4. It will also take that form when player 1 prefers y1 to outcome y4 and player 2 prefers y4 to y3. We would observe y3 if we had the full data generating process in the cases where player 1 prefers y3 to y1 and player 2 prefers y3 to y4, and we do observe y4 as the only observed outcome when player 1 prefers y4 to y1 and player 2 prefers y4 to y3. What's important to note here is we only observe y equal 1 in the case that the true outcome of y4 is taken, where we see player 1 choosing action A and player 2 choosing action B. So as you can see, the action of player 1 depends in some way on what player 2 does, but we don't see that true outcome. We only see if y4 is present. From the perspective of the analyst, I specify the model in the following way. We're creating the utility for y1 is going to be one regressor and an unobserved term. The y3 outcome is going to just be an unobserved term for player 1. Player 1's y4 outcome, you can think of this as the war outcome from the Civil War example, is going to be a regressor that's unique to it, as well as a regressor that's common to both player 1 and player 2. Finally, player 2's y3 outcome is just unobserved, well, their Y4 outcome is going to take the form of a unique regressor to player 2 and a common regressor to that same common regressor that I noted earlier. In each case, the beta is going to have a value, the true beta is the value of 1. The x's are drawn from a normal distribution, a standard normal, as are the unobserved outcomes. I run 2,000 simulations with 5,000 observations each in the Monte Carlos. To more clearly identify the model specifications that I'm using, the strategic probit with partial observability, we're again only we're predicting the Y star, the latent process that we see the joint outcome as the probability of action A and the probability of action B. And this is going to be where the probability of action B is those two regressors, the two kind of war outcome regressors if we're thinking of the Civil War model, where it's a normal distribution, so this is following this backwards induction process. And then the probability that player 1 chooses action A is going to depend on the probability that player 2 chooses action B. As you can see, those are multiplied through the regressors x14 and the common x. And then we subtract off the weight that they hold for the status quo outcome. The denominator in each case is some level of uncertainty. And again, we only see y equal 1 if our y star is greater than 0, so the two zeros are still pooled, essentially. The split sample model is specified as having a zero inflated or selection equation of y star subscript s. This is going to be x prime, so that the beta will still be a positive number, that it will be 1. So we're taking kind of the opposite of x in this case. And to give it a better chance of holding up against the strategic probit, I include the common regressor in each equation, both the selection equation of the y star subscript s and the y star outcome equation, which includes then all of the kind of y4 regressors or war outcome regressors. And the model only predicts that we're going to have a y equal 1 when both stages are expected to have y equal 1. So when y star subscript s is greater than 0 and when y star is greater than 0. Finally, I compare this also to a binary probit where we essentially just include all of the regressors and throw them in the way that we typically see in a lot of analyses. In this case, I again use x prime to kind of have the status quo outcome flipped so that the beta will be 1 and be comparable to the other models. And it's important to note that in this case, there will only be 4 betas predicted because the common regressor to player 1 and player 2 can only produce 1 beta. They're just lumped together. All right, so comparing the estimated coefficients, we see on the y-axis the kernel density of each outcome, and on the x-axis we're seeing the values that the beta may take. The black line represents a traditional probit, the green line represents a split sample probit, and the red line represents a strategic probit with partial observability. In this case, we see that the strategic probit is able to correctly capture the true value while neither of the other two models are. The traditional probit is going to be farthest away. It's going to have a conservative bias towards 0, whereas the split sample probit will always outperform the traditional probit, but not do as well as the strategic probit because it doesn't account for that conditional relationship between player 1 and player 2. It's also worth noting that in the x subscript c beta subscript 14c, there is not a traditional probit coefficient because, again, the traditional probit can only capture that common regressor 1 time. More quantitatively, we can look at the recovered coefficients of the models and compare them also to the root mean squared error. We see that in this case, the true value of the coefficient is going to be 1. So I report the probit, the split sample probit, and the strategic probit. The strategic probit is in red so that you can see that it is always closest to 1. The other models are always biased downwards in a conservative manner. The root mean squared error gives us the same general accounting as the previous slide, showing us that the strategic probit always outperforms both the split sample probit and the traditional probit, with the split sample probit always performing second best. In terms of model fit, I run a Clark's distribution pretest, which takes the median log likelihood from each individual observation. In this case, you can only compare one model to the other, so I'm always comparing the strategic Probit to first the Probit model and then the split sample model. Higher values are indicating that the strategic Probit is outperforming on the individual observation the alternative model. In this case, we see evidence supportive of the strategic Probit performing best. Using the Long test, we also see evidence of the strategic Probit performing best. And if we start looking at predictions of correctly identified individual cases, we see that the split sample and strategic Probit perform about the same on predicting the overall outcomes. We see that if the Y actually was 1, the traditional Probit model actually performs best. But when we turn to the false positive count, we can see that this is because it is predicting far more cases to be 1 than is actually true. Finally, if we want to know how many of the unobserved if we want to separate the two zeros, we can correctly predict about 40% of the unobserved Y3 outcomes, where the other two, the traditional Probit and the split sample Probit, cannot predict those at all. I also I test this model to its robustness to misspecification. It's been claimed in previous literature that strategic models are especially problematic in that they can send bias from the player 2 kind of equation, and that this will affect estimates of player 1, that these are especially sensitive to misspecification. To analyze this, I'm going to look at 3 types of misspecifications so that the data generating process is unknown to the analyst, since we in reality don't know this. So I include first a spurious regressor. I'm also going to misattribute one of the regressors and put it in the wrong player's utility. And then I'm going to misplace one of the regressors for player 1 in the wrong utility for player 1 and actually double count it into 2 utilities. To demonstrate this misspecification, we see that the overall model is the same as before, with the exception of these blue regressors that I'm now including. So from the true data generating process, it's the same as before, but I'm now including, from the perspective of the analyst, these blue equations, where the first one is going to be this misapplied regressor. This should really just be in player 1's Y4 outcome, and it's being misapplied to player 1's Y1 outcome. I include a spurious regressor, this X subscript S, beta subscript S, in the player 1's Y4 outcome. That one should simply not be there. And finally, in player 2's Y4 outcome, I'm including a regressor that should really only be in player 1's Y4 outcome and should not be attributed to player 2 at all. So what effect does this have? So in this slide, you can see the true value of the equation indicated as either 1 or 0, and the coefficient that's being attributed to that. In this case, we see that the misspecified X variable in player 1's Y1 equation is showing up as statistically significant, and this is obviously problematic. The spurious regressor and the misapplied regressor from player 1 going into player 2's equation, each of those are statistically insignificant and don't seem to be too problematic. In terms of the sample fit statistics, we're seeing essentially the same values that we saw before. So I want to highlight this problem that we're seeing in the misapplied regressor of X14 that should not be there. So we're seeing that it's robust to the spuriousness, but we're seeing that this misapplied regressor in the wrong utility is very problematic, that we're getting a statistically significant incorrect result. And that in the, just going back to the slide again, the true value, where it should be 1 in the correct equation, is now being undersold. This is making 2 coefficients incorrect. I want to note that while this is a problem in terms of estimation, in terms of recovering the correct coefficient, theoretically, this would not lead to an incorrect inference, in that we're using a random utility model, so that while the utility of the Y1 for player 1 is incorrectly is moving, we're making that in reference to the utility that they would have from that Y3 outcome, or from the Y4 outcome. So since we're using a random utility outlook, it's going to be the weight attributed to each utility that matters. So in this case, this variable, while it's being undersold in one equation, it's being oversold in the other, and it would lead to the same theoretical inference. I also want to note that using the same regressor in two of player I's equations, or in this case player 1's equation, is actually very rare. In fact, in my literature review where I look at every political science application using a strategic model, I could find no cases where anybody took the same regressor for the same player. It's very common to take the same regressor across two players and say that it affects each player in some way, but to take the same regressor and stick it in player 1 in two of player 1's equations, I have not seen at all. So this leads me to think that the model overall does a pretty good job in terms of misspecification. I finally want to look at an empirical application using this model. I'm going to replicate Fearon and Laitin's 2003 article looking at Civil War onset. This is one of the most frequently cited articles within the Civil War literature, so I thought it would be a good test, and it has a nice, it's a very nice article in that the authors do a great job of arguing how they think each variable will actually influence Civil War onset from both the prospective insurgents and from government perspectives. So they go through theoretically and say that each of these variables have distinct effects on the likelihood of Civil War outcome. But empirically, they use a binary model. They just run a simple logit. And this using logit is going to create a problem in that they're going to have difficulty in identifying the causal mechanism of their theory. So they theorize that GDP per capita can represent a couple different mechanisms within their model. First, it can represent opportunity cost to rebel recruits, that rebel recruits, as countries' GDP per capita increases, rebels are giving up more to join an insurgency, so it's going to be more difficult to recruit people to engage in that insurgency. At the same time, they theorize that GDP per capita may represent a deterrence effect by the government because it represents government strength, that this is the police and the military. And theoretically, they say each of these processes could be at play, but they're unable to, using a traditional logit model, identify which of these seems to be the driving causal factor. So which of these should actually is correctly identified. And there's a debate then within the literature where they tend to argue, Fearon and Laitin argue in favor of this deterrence argument, whereas Collier and Hoffler and some others argue more in favor of this opportunity cost. The benefit of using the strategic Probit with partial observability is that we can take this opportunity cost argument and say that GDP per capita is one of the observable regressors in the rebel status quo equation, whereas we can take that same GDP per capita variable and put this in the government strength, the government war utility equation, and try to identify which of these mechanisms is really driving this result. So I convert Fearon and Laitin's model from a logit into a probit. You get the same general results as you would expect. This is on the left-hand side of the screen. On the right-hand side, I have the strategic probit with partial observability. You'll note that while there are many more betas being estimated, many more coefficients estimated in the strategic model outcome, this is because we're repeating some of the same regressors. We're putting them in player 1's equation, some of player 1's outcome equations, and some of player 2's utility equations. So in this case, I highlight in red the GDP per capita because I find this to be the most interesting variable in terms of what is this true causal mechanism. And again, in the Fearon and Laitin model on the left, GDP per capita is negative and statistically significant, so it seems to have a pacifying effect overall, but we can't tell if this is due to opportunity costs or if this is due to deterrence. Using the strategic probit, we can try to separate these into a series of equations. So the first three equations are going to be the value that rebels are placing on each outcome. So the status quo equation, an acquiesce equation, and the Civil War equation. And then the last equation is the government's utility for Civil War. And what we see here is in the rebel status quo equation, we're seeing a positive coefficient, which indicates that GDP per capita increases the rebels' value that they put towards the status quo. So this makes them less likely to want to initiate a conflict because they value the status quo more than they would have otherwise, all else equal. So we see some evidence for this opportunity cost argument that Fearon and Laitin noted could be coming from the GDP per capita variable. In the government civil war equation, however, we see that GDP per capita is statistically insignificant, and this would indicate that this deterrence argument has less support, or we at least don't find any support for that in this case. Looking at some of the fit statistics again, it's interesting to note that the Clark test and the Vaughn test are actually making opposite predictions of which model is best, which may indicate that when we start changing from different functional forms rather than just including non-nested models, that these different tests are problematic, and this might be a good avenue for future research. In terms of model fit, we see that in this application, both of them correctly predict a lot of cases. That's because civil war is rare, so if you predict 0, you're going to do great. Neither of them do a very good job of predicting actual observed cases of civil war, which suggests that most of this is cross-sectional rather than in the data, that it's mostly cross-sectional, most of the variation, so we're not doing a very good job of picking when a civil war will actually occur. If we change the threshold for observing a civil war for each model from in the strategic model, if instead of saying we actually have the utility of war being greater, that it has to be maybe twice as much as the status quo outcome for the rebels, or something along those lines, when we start changing those thresholds, or for the Probit that it's predicting war only at maybe a 10% rate, that if we count that as a correct prediction, then we find that the Probit model starts to over-predict and have greater false positives, and the strategic model will outperform the Probit model in those ways. Moving to the predicted probabilities of each outcome, I want to note that the y-axis here is the probability of an outcome. The x-axis is going to be changing the level of GDP per capita. The solid line is the war Probit outcome. The long dashed line is the war outcome predicted from the strategic Probit. The thick dashed line is going to be a challenge outcome predicted from strategic Probit, and then the short dashes are going to be a government acquiesce outcome predicted by strategic Probit. What's interesting to note here is that the war outcomes are essentially the same. So you might say, well, why are we bothering with running these additional models? Or what's the benefit then from the strategic Probit? Well, I would argue that the benefit is that we can actually make predictions about these challenge outcomes and government acquiesce outcomes. We can garner more information from the strategic Probit than we can using a traditional Probit. We can both analyze the causal mechanism, as we've shown earlier, of trying to parse out what GDP per capita actually represents, and we can use this information to start gathering more data on if we think an opposition group is likely to challenge the government at all, and cases where we find that other qualitatively distinct form of 0, where the government acquiesces to an opposition group. So in sum, just our reanalysis of Fearon and Laitin, we find that GDP per capita seems to affect opportunity costs more than deterrence. From a substantive standpoint, we can now this model helps us distinguish between the two types of non-conflict outcome. This helps us kind of analyze arguments of legitimacy compared to appeasement, and we can look at cases that engage in each of those. These challenge probabilities can also be used for future research in addressing dyadic civil war outcomes. In current dyadic civil war outcomes, where we're looking at maybe rebel strength compared to non-rebel strength, we're selecting essentially on the dependent variable. We have to observe the civil war to find this dyadic analysis in the first place for there to be a rebel strength to look at. So this model helps us select potentially the pool of an appropriate sample that may observe a civil conflict in the first place, as we might expect that rebel strength is correlated with rebel winning in some way. We also can identify a pool of cases that are likely to escalate or that may have been resolved through nonviolent means. This could help us from a data collection standpoint of pinpointing cases instead of trying to look at the entire universe of cases. So if we're doing a correlates of war type of data gathering effort, instead of looking at cases of every country in the world where some of them might have a very low probability of anything conflictual occurring, we can focus in on those cross sections that are more likely to have a conflict, and this might help us for some of our language, overcoming some of the language issues, and that we can kind of pinpoint cases that tell us what languages we need to use or which newspapers might be most appropriate. And finally, this lets us look at civil wars, just one kind of broader outcome of opposition and government interaction, and that these are tied, that there's a selection effect here that is strategic. So the model is beneficial in that it helps us build strategic empirical models even when the data is not set up to really permit this, as in the case of Civil War that I just used, as well as being potentially applicable to crisis escalation, intra-party discipline in legislatures, regulatory regimes, as the EPA example suggested, as well as numerous other potential cases. So with that, I'd like to thank you for your time and open up the floor to any questions that you might have. Thank you.
All right, Mark, thank you very much for that presentation. At this point, Mark's available to take questions from the audience. You may call in to ask a question on the air at our toll-free call-in line. Let me actually put this on the screen here. 1-855-667-8287. That's 1-855-NO-STATS. You can email questions to methods.colloquium@gmail.com. Finally, you can ask a question using the GoToWebinar Ask Question box that appears on the GoToWebinar control panel. For viewers outside the United States, we recommend using the Ask Question box to ensure that we receive your question immediately. So while we're waiting for some questions to come in, I have some questions that I was thinking about while you were giving your talk. So I think the first and sort of simplest question is, if you do not want to program this on your own, but you want to use it in Stata or R, is there an Ado file or an R library that will implement this for you?
This project is actually forthcoming at Political Analysis, and in the article I do give some Stata code that I made available, as well as the replication file has Stata code that can help you if, in some cases, these can be difficult to get to converge, so you may have to use specifying initial conditions, and I have a process for that that's outlined in the replication file to make this a little bit easier, but there is a Stata version of the code available.
And I saw in the back of your paper there's a program, but it looks like it, I mean, most users want to just type, SSE or as SSC install strat probit or something, and that's it.
Right. Yeah. I'm still in the process of coming up with a more user-friendly version of this.
Okay.
It's a relatively recent project, so I'm still, in terms of coding things for other people's applications, I need to make it a little more general, but I'm in the process of developing that.
We have a question from Toby Heinrich. Have you compared the estimator against fancier other estimators? Signorino and Kenkel's polywog seems to be the obvious comparison here. These authors simplify the likelihood even more compared to the theoretical model benchmark, but allow for much greater flexibility in the linear predictor.
I have not compared it to polywog. I've talked to Kurt a little bit about, Kurt Signorino a little bit about how these might compare. We think that they would give relatively similar estimates. However, the benefit of this setup is that you're actually fitting it to, or what Kurt would probably say is the benefit of his is that it's more flexible. The benefit I think that comes from this setup is that you're fitting the theory that you actually tend to develop to the data itself. We have a lot of strategic models that we're going to be trying to say what the causal mechanism is from the actual equation, and we're able to do that in this approach, whereas using something that's more flexible like polywog, you're still going to have to interpret when you think those nonlinearities should be entering into place. You're not simply saying the utility from player one of this outcome, that this is how that variable actually affects that outcome. Polywog, you're going to have to interpret some of those nonlinear relationships in a less straightforward manner. So I think the benefit of this is using that more structured approach.
One of the things I was thinking of, because at the end you were talking about how what this procedure does is it allows you to draw inferences about challenging and acquiescence.
Right.
And as you said in the beginning, those are not observed. So you're in a position of drawing inferences about outcomes that you can't observe. So there's, in some ways, you can't be tested, you can't be checked. There's no way of, for example, comparing cross-validating the predictions of the model. It also means that the inferences, by definition, have to be strongly theory-dependent. In other words, those inferences are coming directly from the structure of the model, not necessarily, they're not coming from the data. They're in some ways not identifiable from the data. So I'm wondering what the consequences are for that when somebody writes a paper and says, oh, I'm going to test a theory of, challenging and acquiescence in civil war. They use your model, they come to some conclusions. Have you just confirmed the theory with itself if you draw conclusions that assume the structure of the theory is correct?
Well, I would take it kind of the other direction. This helps us collect data on those cases and pinpoint our data collection efforts rather than it provides avenues of where we might actually find these cases and might help researchers in using their NSF grant to the best possible way as opposed to not knowing where to look in the first place. It could also help policymakers on which types of firms do we need to really be targeting rather than going off some of these prior assumptions where we have this might be a dirty industry, but we don't actually have any evidence that these groups are acting in a that they're lying to us in their regulatory behavior. But this helps us just pinpoint those and helps us look at the cases that can help us cross-validate this. That I wouldn't want to necessarily make a claim that the acquiesce outcomes are, I wouldn't want to use that to try to confirm a theory of the acquiesce outcomes. However, I think it does provide us a little bit greater leverage than when we're doing this already essentially with a traditional low jitter probit where we say, oh, well, see, this variable is negative, so that means it's having this effect. Well, we're actually being more explicit in using this type of a setup as opposed to...
Well, so I'm going to go back to your Fearon and Laitin example where you said, okay, we want to figure out whether higher GDP is really sort of which end of things is it affecting? Is it affecting rebels wanting to go to civil war, or is it reflecting the government's reticence to sort of to push a fight? And that in some ways is proposing and testing a hypothesis, right? Oh, I want to know what affects acquiescence, and the data do inform the result in some way, but not necessarily in the way, if I could observe acquiescence, I would just regress acquiescence against the thing I care about and see if there's a relationship, and then I could see, oh, does my model actually predict the outcome? We don't ever actually get to see the outcome. So in some ways, the inference that rebel preference for the status quo is influenced by GDP is strongly model dependent, and I can see. It's natural that someone's going to take your model and start making these arguments, right? Because that's the natural application of what this is designed to do. And what I'm worried about is to what extent is that a test of that hypothesis, or alternatively, is it a sort of an interpretation of data through the lens of a theory? There are lots of philosophers who say there's no such thing as a pure test of a theory. All facts are theory-laden. But this seems especially theory-laden.
Well, I think a lot of our more advanced estimators are starting to run into that potential danger in a way. Anytime we're using a zero-inflated model, we're having the same exact issue where you're making an equation where you're saying, oh, I think these zeros are following this theoretical process to some degree, and I'm now testing a hypothesis on that, which can't be necessarily split up either. So there's always the potential of some abuse of your theory. However, what I think the benefit of this setup is that you can actually, you're still specifying the theory itself, where I've seen a lot of papers using zero-inflated models, for instance, that say, well, this is strategic. This zero represents deterrence. This zero represents some kind of acquiescence, but they're not actually then modeling the strategy within the estimator itself. This is just trying to allow you to model the theory that you have a little more closely between the empirics and the theory, but the potential for abuse, I think, is available in a lot of estimates.
I just want to know how to read it. It's important to know how to interpret this, and whether we can interpret it as I guess the extent to which it serves as a test versus an interpretation of data seems to be a little it's not whether it's abused or not, it's just how do we read it. I have another question for you about the identifiability of your parameters, because you mentioned that when you enter in things multiple times, and for example, when you enter one of your variables in your simulation, you entered it into two parts of the utility function for player 1, I think.
Yes.
You get weird coefficients, and that makes sense because I think it makes sense because the coefficients are only defined relative to one another, meaning they're only the relative gap between them is identified. But that would seem to indicate that putting x in both places makes the model unidentified. In other words, you could get a lot of answers.
If it should identify as long as they're not in each of the outcome equations for that player. The problem is, as you noted, with it being a random utility model, and that they are just comparing kind of the relative gap. That's, in a way, protects from too much of a problem that in terms of the inference that you're making, because you're going to still see war goes down in this case, or something along those lines. But in terms of identification, as long as it's not in each of the equations, it should be able to recover an estimate. Now the problem is, theoretically, why would you ever put the same regressor in multiple of these equations? You would expect theoretically that it's going to affect a utility, typically one utility for that individual player, that it would be very unlikely that the same regressor is going to have multiple utilities being increased with it.
Well, looking at the example you have on the screen right now, I don't know if this is true, but I could tell a story where the GDP per capita affects the rebels' preference for the status quo, for the reason you said. It also affects their preference for civil war, because maybe it's a proxy for state capacity, so maybe it's in some way measuring how likely they are to win. Maybe it captures in some way the prize, in other words, how much are they getting out of executing the war versus not executing the war. So it seems like there are some ways in which we could think, okay, well, GDP has this effect on this decision, and then sort of on the next decision has a different impact.
Well, it's actually the GDP per capita, the chance of winning the war is already being captured by accounting for the government's utility for civil war. That this would capture that deterring effect, that if the GDP per capita of the state, if its state capacity is higher, this is accounted for within the regressors of all of the rebel outcomes, the incentive of fighting, and that this deterrent effect would reduce the utilities that the rebels have for fighting in the first place. So the probability of winning is already accounted for. In terms of the prize, I think that one's pretty interesting, but typically within the Civil War literature, the prize is a lootable resource, which is, at least in Fearon and Lane's case, they represent with this oil exporter. And we typically don't think that these groups want the state for the sake of having the state. They want the state for some commodity that they can take and profit from. So in that case, theory would have to guide you to some degree. This isn't a cure-all that you throw every regressor into every equation. It is structured in the sense that it is not, as Tobias noted, it's not as flexible as some other estimators. It is very theory-driven in that sense.
And what I'm getting at here is it might be the case that in terms of writing a program and presenting the model, if all of these things are so in other words, if you think of a two-stage game, if the first player's move, they're considering, okay, if I go left, I get this. If I go right, then there's a probability that the government does this, and then there's another probability that they do the other thing. Ultimately, it might be okay to just put all the regressors for the rebels or for the first player's move into the utility for sort of, I guess in this case would be civil war for the rebel outcome, because that's going to be a probability weighted gap anyway. In other words, what do you gain by putting the same thing into the status quo? Because instead of subtracting A minus PB, now you're just saying, well, it would be something like 0 minus PB over A. In other words, you're just sort of normalizing them.
Right. Signorino and Terrar talk about that in their 2006 piece, where they do say you could put all of the regressors that you want in the in the Y4, or in this case the Civil War outcome, and then you'd be normalizing the other two and holding them constant at 0 and 1, for instance. You could do that. There's no reason not to do that. We have some theories, though, that might be more explicit in saying, I think this is a status quo type of response, and that if we normalize this, you're not putting on difficult restrictions, but you are putting restrictions on the model that otherwise would not exist. And if we want to, we're already putting a fair amount of structure in it by having this kind of two-step process in the first place. So in the case of the Fearon and Laitin, they do explicitly talk about how democracy should pacify, or operates as kind of this opportunity cost for rebels, and that this instability operates in that way. So I put them in those equations. If you put them all in the Civil War I, it shouldn't be too problematic, but I tried to follow the theory as closely as possible.
We have a couple of other questions from viewers. So a question from Ara Wu. In your firm example, the firm chooses to pollute and then also chooses to hide information. In other words, there are multiple or two strategic decisions going on. Sometimes rebels can make demands publicly, and this is going to the Civil War example, or they can decide to make demands secretly. One is an alternative for the other. So in this case, do you think it will affect drawing causal inferences if there's sort of multiple ways in which, in other words, if the decision to hide is also itself strategic?
Well, you could, in this paper I'm presenting kind of the most simple strategic model. You could, of course, have more nodes and more steps, and the problem that you're going to run into is if you don't have data on each one of those steps, you're going to be passing along greater and greater uncertainty through the model. But this shouldn't be a problem in terms of kind of theoretically you can still estimate this model. It's just going to become more and more difficult to have any level of certainty and draw those inferences out. The benefit of this model is that you can at least attempt to do that, or you could have missing data on certain steps in the overall kind of strategic model that you have, that you can have some nodes that are missing data, that you can still probabilistically estimate those, as opposed to the kind of current strategic Probit setups that require you to have data on each actor choice at each stage. So in terms of the causal inference, you expect there to be just greater uncertainty for those earlier stages, but there's nothing saying that you wouldn't be able to still, if you have sufficient power, still find evidence in favor of your theory.
I think this kind of answers Tobias asked, or Toby asked another question. Any thought on what happens if we have a longer game tree but still just a binary outcome? In other words, if you add more nodes to the beginning of the tree.
Yeah, it's much the same answer. You're going to be just increasing the level of uncertainty that you have because you are probabilistically estimating something, as opposed to having data telling you that yes, that your likelihood is getting closer to the actual response at each node. We're just adding to that uncertainty as we go farther back. So if you go too many stages back, it's going to be really hard to find anything on your on some of those earlier positions. But that's the same problem that we would run into in having a strategic model that kind of in general. Right now, we would, with that strategic model, we would just ignore the structure of the game altogether because we can't estimate those stages with missing data at the node, essentially. So at least now we're trying to gain some leverage on that.
Well, we're about out of time, and all the questions have been answered. So I'd like to take this opportunity to thank Mark. Thank you for being on the program today. Next week, we're going to have our last presentation for this semester, at least. Noon Eastern, 11 o'clock Central. It'll be a presentation by Mike Ward of Duke University entitled "Irregular Leadership Changes in 2015: Forecast Using Ensemble Split Population Duration Models." You can go to our website, which I will now flash on the screen, www.methods-colloquium.com to get more details about that presentation. Thanks, Mark, for being here.
Yeah, thank you for having me, and thank you for all the great questions.
Thanks, everyone, and I hope to see you next week.